Hi everybody, we are starting chapter 19 with this video. This is recording 19-1 and with chapter 19 is on carbanions 2 or carbanions part 2, and all we have left is chapter 19, chapter 20, and we are all done. 2 semesters of organic chemistry. So in chapter 19 we're going to be looking at 3 different types of reactions. We're going to be covering the Claisian condensation, which you are responsible for the reaction only. The aldol condensation, which we've already seen in lab, and you'll be responsible for the reaction and the mechanism. And then finally a spin-off from the aldol condensation, and that is the Michael addition reaction. And again, you'll be responsible for the reaction and for the mechanism. What you're going to see in the Claisian condensation and the aldol condensation is that these are essentially nucleophilic acyl substitution reactions, where the nucleophile is going to be a carbanion, and the acceptor, as it always is in NAS reactions, will be a carbonyl group. So let's start out by first looking at the Claisian condensation. And in the Claisian condensation, the overview tells us, or is going to show us, that essentially what we have are 2 esters coming together in the presence of base, usually as a catalyst, and forming a bigger ester and an alcohol as a leaving group. So let's just dig right into an example. So here we have our 2 esters. Note that on these particular esters, each one has an alpha carbon, so we can form the carbanion at either one. I'm going to put a dot on that one, so that's going to be our carbanion. Meaning that for this reaction, that's also going to be our nucleophile. And that nucleophile is going to add to the other ester. So this is going to be our acceptor, since it is going to accept the nucleophile. And the nucleophile, of course, add to the carbonyl group. This will be an NAS type of reaction. It is base catalyzed. Again, you're not responsible for the mechanism here. But what's going to happen is you're going to form a new carbon-carbon bond. These 2 dots are going to come together, and everything we see right here is going to be your leaving group. In NAS reactions, we have a nucleophile, adds to a carbonyl, and something has to leave. So if we follow this through, we see that in the product, the 2 dots are going to be right here. That's the acceptor part. The other dot here, which is the nucleophile part. Here is our leaving group down below. And let me just put a little dotted line going through one of these dots so that I can label on the right side the nucleophile piece and on the left side the acceptor. And essentially that's all you're going to be responsible for knowing for the Claisian condensation. Since I did not really focus on the mechanisms of base catalyzed or base mediated NAS reactions back in chapter 18. All I want you to know is this reaction. So again, you've got 2 esters coming together to form a bigger ester. One of the esters will act as the nucleophile. The other ester will act as the acceptor, which will also have a leaving group. So here's another example. So this is a Claisian condensation, and since we're covering these towards the end of the semester and you're only going to see these on the final, what I will do is I will always label these last set of reactions that we're going to be seeing, so you'll have an idea of what you're looking at. So in the Claisian condensation, one of these must be the nucleophile, the other one must be the acceptor. If you carefully examine these 2 esters, you will see that only one of them has an alpha carbon with hydrogens. The ester on the left, we have an alpha carbon, but there are no hydrogens here. There is no way that this can be your nucleophile. So this ester is your acceptor. meaning that the nucleophile will add to the carbonyl group, and that part is going to be your leaving group. The ester on the right, we notice that we do have an alpha carbon that has hydrogens. That's going to form your carbanion. That'll be your nucleophile. So again, we put these two dots together. We're going to have NAS, nucleophilic acyl substitution, the leaving group leaves. And if we carefully draw our product, all we have to do is put the two dots together. So here's the first dot. I've drawn the leaving group not being there. The leaving group's going away. If we want, we can draw it down here. We connect this to the other dot, and for the nucleophile we draw in everything. So in essence, that's all we have for the Claisian condensation. Now, as we've seen with many reactions, you can also have intermolecular reactions. So here's an example. If you want, you can give it a shot. This is an example that we'll be seeing on the next worksheet that we'll be doing in class. Identify the location of the two carbonyl groups. Figure out which carbonyl group has a carbon, an alpha carbon with hydrogens. That's your nucleophile. That automatically makes the other carbonyl group the acceptor. Put a dot on the appropriate carbons, and then just combine the dot. If you add up the number of carbons between the two dots and including the two dots, that'll tell you how many carbons are going to be in the ring, and it's always going to be a ring of either 5 or 6 carbons. But I'll leave that example up to you, and that example, as I said, we'll see on the next worksheet in class. That's it for the Claisian condensation. All right, let's take a look now at the aldol condensation. And this is a reaction that we had seen in lab earlier this semester. And you're going to be responsible for both the reaction and for the mechanism. So in the aldol condensation, as we are on chapter 19 and chapter 18, in many cases dealt with carbanions. The carbanion will act as a nucleophile. And remember, the carbanion is the carbon alpha to the carbonyl group, and it has to be a carbon that has hydrogens on it. That'll form the nucleophile, and in this case it's going to add to an aldehyde or a ketone. So the aldol condensation is not strictly a nucleophilic acyl substitution reaction. It's a little bit different. We do get an elimination. The unusual aspect about this is that we're going to see hydroxide as a leaving group. We have to understand why hydroxide can be a leaving group, since we want our leaving groups to be a weak base and hydroxide is a strong base. And these are base catalyzed reactions. So here is a general example for aldol condensation. We have, in this case, 2 ketones. One of these ketones has to be the carbanion. I will make this one the carbanion. We've got an alpha carbon that has hydrogens on it. Meaning that's the nucleophile. And the other aldehyde or ketone, the other carbonyl, is going to be the acceptor. We see we have base catalyzed, and when you look at the structure of the product, you're probably wondering how in the heck do we get that if you don't remember seeing this from the lab. But let's just trace through what happened here. This carbon, where I'm putting the dot, is the carbon of the nucleophile. That's where the carbanion originally formed. The carbon-carbon double bond represents a new bond between this dot and this one. And since we are doing an elimination of hydroxide, we end up with a carbon-carbon double bond. So in the aldol condensation, wherever you see the carbon-carbon double bond in the product, that tells you where the carbanion added to the acceptor. Notice the acceptor has 1, 2, 3 carbons, and we have 1, 2, 3 carbons over here. So just put a little dotted line through the carbon-carbon double bond, because that's the new bond that was formed. So this is an unusual reaction, and not only did we form a new carbon-carbon bond, but it's a carbon-carbon double bond. So on the left side, we have the nucleophile part, and on the right side, we have the acceptor part. And we're getting water as a product. So the product that we form in an aldol condensation is a alkene that is conjugated with a carbonyl group. Usually it's going to be that of a ketone, and the product is referred to as an enone for alkene and ketone. Okay, I don't use that terminology in naming this. Okay, I just want it to be obvious to you that the product that we're forming is an alkene and a ketone. All right, so let's take a look at the mechanism for this reaction. And this is a base catalyzed mechanism. Notice that we have a strong base as our catalyst. And whenever we have a strong base or a strong acid, we almost always use that in the first step. So step 1, we have to form the carbanion. So I'm going to draw in this carbon, I'm going to draw in the 3 hydrogens. So this is the carbanion part. The base catalyst is going to grab one of these hydrogens. Electron pair gets left behind on the carbon. And these steps are all, for the most part, again, equilibrium steps. And I'm going to put the dot in. We want to keep track of the dots that were coming together. And we form our carbanion. Remember, the negative charge is conjugated with the carbonyl group, so it is delocalized. That's why these alpha hydrogens are actually acidic. And since the base grabbed a proton, we're forming H2O in this step. So, step 1, proton transfer, base catalyzed reaction to form the carbanion. And now the carbanion will do what we want it to do, which is to be a good nucleophile. So in step 2, we redraw the carbanion. And I'm going to also redraw the other carbonyl compound, but I'm going to lie it on its side. So it'll be a little bit easier to see what is happening here. Put the dot on that carbonyl carbon. And here we're going to have the carbanion. We'll add to that carbonyl carbon, push a pair of electrons onto the oxygen. Typical addition reaction to a carbonyl group. And in this step, we've actually formed the new carbon-carbon single bond. The electrons went on the oxygen, so it must have a negative charge, and just put in the rest of the bonds to that second group. All right, so there's our initial intermediate. The key point here is that we formed the new carbon-carbon bond. Now we've got to do a series of proton transfers. What we need to do is this oxygen that I'm circling, we have to convert into an OH and then have it leave. So step 3, we're going to start heading in that direction. We formed water in the step above, so that's going to be the proton donor or the acid in order to protonate that oxygen with the negative charge. So let's bring the water back, and that water's not done. We're going to be using that again, or forming it again, I should say. So the negative charge on the oxygen is going to grab that proton. Notice what we're doing here is actually regenerating the hydroxide, which is the catalyst. and we form this intermediate product called an aldol, which is actually somewhat stable. It can be isolated. Normally we do not run this reaction under conditions in which the aldol is isolated. So again, the base form of the aldol has grabbed a proton from water that has protonated the aldol, making it more stable and giving us hydroxide catalyst again. And we need this hydroxide because what we have to do now is grab one of the protons from this alpha carbon, and those electrons will come in to form the double bond and also eventually push out the leaving group. Now, one difference in this elimination reaction that is different from the NAS reactions is that it must occur in 2 steps. Since we're forming a carbanion, you have to form the carbanion first, and then in a final step, the carbanion will push out the leaving group. So, step 4, we're going to form the carbanion again. So the carbon alpha to the carbonyl group's got 2 hydrogens. We're going to use that hydroxide once again, or for a final time, grab one of those protons. Those electrons get left behind on the alpha carbon. This gives us our carbanion. And remember that steps 4 and 5 must be done in 2 steps. Experimentally, it is known very clearly that these 2 steps occur, and they don't occur concertedly. They do not occur as once. And finally, now here's our water byproduct that we saw in the balanced net equation, and our carbanion. And that's a stable carbanion. That's why we must show this in 2 steps, because this carbanion is stabilized by the carbonyl group. And now in our final step, we do an elimination. Step 5. And I know this video is going long. It's going to hit 20 minutes. That's because the mechanism takes a while. And this last step is important because not only is it an elimination reaction, these electrons come in, but in pushing out hydroxide as a leaving group, we are actually reforming the catalyst, which of course you must do in a catalyzed reaction. So that gives us the double bond between the 2 dots, and reforms the catalyst. Now, why is it we can have hydroxide as a leaving group here? And the reason has to do with the product. We have a conjugated product. Whenever we see conjugation, that's usually a stable form of an organic molecule. So it's the conjugation here that actually drives this step and makes this equilibrium actually favor the products. So this gives us our enone. It allows us to have a strong base as a leaving group because of the conjugation between the carbon-carbon double bond and between the carbonyl group. So just to wrap things up here, I've got 2 more examples. One is going to be, and you'll see this, you can use this example and work it through. You'll also see this on the next worksheet. But can we work backwards? Can we start with the enone product and figure out what the reactants might have been? What are A and what are A and B? So again, look at your product, the carbon-carbon double bond, that's where the new bond was formed. The dot closer to the carbonyl group, that tells you that this piece on the left was the carbanion piece, and the piece on the right was the acceptor. It was the other carbonyl. So based on that, you should be able to figure out the structure of A and B for the reactants. And one final example you can do for practice will be an intramolecular aldol condensation. So here again we have a molecule. It has 2 carbonyl groups. You will notice that, let me see, usually in these intramolecular reactions you're always going to form a ring that's going to have either 5 carbons or 6 carbons in it. So you have 2 possibilities of alpha carbons that might form the carbanion. Okay, the one on the left and the one here on the far right. You have to figure out which one of these alpha carbons is going to be the one that's actually going to form the carbanion, so that when it adds to a carbonyl group, you'll end up forming a ring that has 5 or 6 carbons in it. So I'm going to leave the identity of this product up to you, and once you come up with that product, it would be good to practice the mechanism. Okay, so that's the end of video 19-1. We'll have one more to go for chapter 19, and that is the end of this recording.